Hello, this is Jeremy, and in this video, I'm going to talk about how to do a chi-squared test when you're testing something about the variance or the standard deviation. And so I want to explain a little bit about rejection regions. Maybe you've used rejection regions for the mean or for the proportion, but just in case, I'm going to talk about it here with the chi-squared distribution. So the chi-squared distribution is a right-skewed distribution, so it's a little different than your typical normal distribution. So when we have a left-tailed test, we're going to put alpha on the left-hand side of the distribution. And so we're going to try to figure out what this cutoff is that would have an area of alpha to the left. Now for a right-tailed test, we're going to do essentially the same type of thing. We're going to create a rejection region over on the right. We're going to stick alpha over here, and we're going to say, what's this cutoff that would have an alpha area over to the right? And for a two-tailed test, we're going to take our chi-squared distribution. We're going to put half of alpha over here. We're going to put half of alpha over here, and we're going to look up two different cutoffs. So two different cutoffs, and we're going to say what cutoff would have half of alpha area to the right, what cutoff would have half of that to the left. And so this will be important to pay attention to the table, because in the table, unlike normal distributions, the chi-square distribution tables actually show you area to the right. So you have to kind of reverse things when you're looking at anything else. So the procedure will be, we calculate a test statistic. If it ends up in the shaded region, we reject. If it ends up in the other region, we fail to reject. Okay, so let's try it out on an example. So in this example, we're told under an old computer system, the standard deviation of waiting times in the ER was 0.5 minutes. Okay, a new system's been implemented, and in a random sample 25, the standard deviation was 0.7, which seems to have increased. Okay, well, at a significance level of 10%, is there evidence to say that for the whole population of times, the new system has increased the variability? In other words, the population standard deviation or variance, assuming the waiting times follow a normal distribution. We need that to conduct a chi-squared test. Okay, so my claim, my statement that I'm testing has to do with the variability of waiting times. Has it increased? So we want to know, has the variance increased from what it was before? Well, what was it before? It was 0.5 for the standard deviation. So this would be 0.5 squared, which is 0.25. Okay, and so the complement to this would be standard deviation is less than or equal. The variance is less than or equal to 0.25. So our null and alternative become the variance is less than or equal to 0.25. The variance is bigger than 0.25. Okay. Now, it isn't necessarily difficult to get a p-value to do this test. The problem is that most standard calculators won't do it, so we're usually going to use a rejection region here. So what we need to figure out is what our rejection region is going to look like. Now, this is a right-tailed test because our HA is a greater than. So we want to place the area alpha out here, which would be 10%. We want to figure out what this cutoff would be. Okay, well, what I'm going to do is look on the table, the chi-squared table, and I'm going to look at n minus 1 equals 24 degrees of freedom. That's going to help me find this. So on the table, I'm looking down at 24 degrees of freedom, and then I want to look at 0.10 area to the right, and I get 33.1962. 33.1962. And make sure you find that on the table. Go down to the row with degrees of freedom 24. Go over to the right where you have area to the right of 0.10 and make sure you're in that column. Okay, what am I going to compare this to? Well, I'm going to calculate a test statistic. And so my chi-squared test statistic is n minus 1 times s squared over sigma squared. Okay, so that's 24 times. S squared comes from our sample. So in this case, that'd be 0.7 squared. Sigma squared comes from our hypothesis. We already squared that before, it was 0.25. So when I calculate this, I get 47.04. So now I say, where is that on my table? Or excuse me, on my chart? This goes to the right and it gets bigger and bigger, so it's out here in the shaded region. Since it's in the shaded region, I reject H0. If I reject H0, it means I like HA. HA is saying the variance is higher. In other words, we do have evidence that the new system has increased the variability of waiting times. So of course I would expect you to fill that in. There is evidence, once again, I'm answering this question, that the new system has increased the variability of the waiting times. So again, this procedure is very similar to that of a p-value in that we have a calculation that determines which direction we're going to go. Now be very careful when you're doing a left-tailed test. You're going to want to figure out the area to the left. So for example here, the area to the left here is 0.9. If this was a left-tailed test, I'd be looking in the column for 0.9 because the total area is 1, right? So make sure that you're looking up the correct value in the table when you're doing other types of tests.